All right, example 2 and 9.3 is really how I would solve a question if I was given the choice for the method to use. We're going to solve this equation graphically, and then we're going to express our answer to the nearest hundredth, and then we're just going to verify algebraically by substituting whatever we get on our calculator into there. Now, the best way of doing this by far is to graph each side as y1 and y2 separately and then find the intersection. You could move these terms to the left-hand side and then look for the x-intercepts of the resulting function. But I find it much easier that if you're given an equation that has variables on both sides, just graph both sides and see where they cross, which is really treating this as a systems of equations, basically. The first equation we're going to look at, and remember, it's more complex than a single term in the numerator. So I'm going to put a bracket around my numerator, and it's x squared minus 3x minus 7. I'm going to divide, and I'm going to put a bracket around my denominator, which is 3 minus 2x. And then my right-hand side is going to become y2, and that's going to be x minus 1. Now, the hope is that Zoom Standard works. And you can kind of see the preview graph down here, and it does. But make sure you're willing or able or capable to change the window settings. Not every single question is going to be nice and pretty on Zoom Standard. The point of technology is that we can quickly regraph this with a lot of time or effort, which is a pretty amazing thing if you think about doing math 50 years ago. All right, so that is our graph. We're going to look at it in a little more detail here, so I'm going to let it kind of graph on the big screen. And because we have plotted, I didn't write it for some reason, but because we are solving when y1 is equal to y2, that's where these functions cross, the intersection point. So I'm going to find that by going second, trace, it's an intersection, so I'm going to use option number 5. And the nice thing about intersections is you can put your cursor on where you think the intersection is, and then hit enter 3 times. Now I'm going to save myself a little bit of hassle, because what the calculator does is when you find an intersection, it's actually stored that value as x. So if I go back to my home screen and type x in, it gives me that value, which is going to prevent me from having to try to memorize an 8-digit number. Okay, we'll find the other intersect as well. I'm just going to move my cursor over to the other intersection. If I can get there, there we go. And then again, because it's on that intersection, enter is the first curve. It automatically switches to y2, and then the guess doesn't much matter. And I get 3.0971. And again, I'm just going to go back to my home screen, and I'm going to put that value there. Now, the advantage of doing that is that allows me to see, in a different location, well, I shouldn't say unrounded number, because this is still rounded. Those decimals are very unlikely to end there. But again, this gives me 10 decimal places. The question only asks for 2. I'm just going to quickly bounce those into my smartboard program here. And then what we're going to do is we're going to do the second part, B, where it asks us to verify these solutions algebraically. And they definitely don't do us a favor, because these numbers are so long, and maybe ugly is not the right word, but they are quite they're not very pretty numbers, I guess, is maybe the way I want to say that. So we have to expect that we're going to get some relatively ugly looking decimals when we verify this. And when we do verify it, we do have to verify both. Don't verify the first value of x and then just kind of hope for the best. But the question asks us to round to the nearest hundredth. So I am going to verify negative 0.43. Now, before we do anything, this is very unlikely to work perfectly. Because I've rounded that number, there's no expectation that I'm going to get exactly the same number on either sides, but there is the expectation that they should be accurate to the nearest hundredth. So the way that I'm going to verify this, I went a little too far there, is I'm going to take that value of x and substitute it in for the x's in the original form. So I'm going to check if negative 0.43 squared minus 3 times negative 0.43 minus 7 all divided by 3 minus 2 times negative 0.43 is equal to negative 0.43 minus 1. So all I've done there is I've replaced the x in this boxed equation with one of the values, the first value that I found. Now, because this is a relatively ugly looking formula, I am going to at least write an intermittent step in here. I would highly recommend that when you're doing this on your calculator, you evaluate the top and the bottom separately and then do the division. And that just tends to avoid some of the calculation mistakes we make. So the numerator becomes negative 5.5251. My denominator, and I'm actually putting this into my calculator right now, so hopefully I do it right. The denominator becomes 3.86. And then on the right-hand side here, this one's a little easier. It's negative 1.43. Now, if I've done this correct, then when I take that left-hand side, what I should get is the right. Now, I really want to re-emphasize that this is not going to work perfectly. When I put this into my left-hand side, I get 1.4313733057, and I say that that's equal to negative 1.43. I just forgot the negative there. Now, that's not perfectly equal, right? Negative 1.43 isn't negative 1.43137, but because I rounded that answer to the 100th, we should really only expect this to be accurate to the 100th, and it is. So because the left-hand side is equal to the right-hand side, again, ignoring that unrounded BS at the back, we know that that's correct. Okay, it does want us to verify both though. I'm just going to try to sneak this in on the bottom. I also have to check and make sure you are sharp with your rounding, because when I look at that other answer, I am going to check 3.10 for the value of x. Because this 7 rounds the 9 up, that in turn rounds the 0 up. All right, so usually students don't struggle too much with the rounding in this chapter, which is good. So I'm going to check if 3.1, I'll try to make that decimal a little bit cleaner to see, 3.10 squared minus 3 times 3.10 minus 7 divided by 3 minus 2 times 3.10 is equal to 3.10 minus 1. Now, really importantly, I'm plugging this into the same equation. The only thing that's changing here is the value of x. And again, we should not expect this to be perfectly equal because we have rounded the number. Make sure you are checking that you can do this on a calculator. There's, not much point in teaching this unless you're actually going to, put in a little bit of time and make sure that you can do it. You're on your own as well. The numerator becomes negative 6.69, and the denominator becomes, I did some multiplication there. Sorry, just typing this in as I go. I got negative 3.2 in my denominator. And when I take negative 6.69 divided by negative 3.2, what I get is 2.090625, and that's equal to 2.10. Now, again, the reason that this is slightly off, and it is more than slightly off, there's a bit of an issue here. It's not rounding correctly to the nearest hundredth, and it's because we've rounded that number up so much. Now, these numbers are very, very close to each other. It's a little bit annoying that they're not perfectly equal, but we could use our calculator to kind of double verify this and, just take another look and make sure we've done it correctly. If you truly want to verify this as well as possible, keep the value of x stored in your calculator, and then when you check it, use the actual function. X squared minus 3x minus 7 divided by 3 minus 2x, and that will work perfectly. But we are going to say that that is verified as well. All right, solving graphically is pretty comfortable for most students. It's the algebraic method that takes a little more practice, and we're going to see that again in example 3.